Hello everyone, this is Professor Konstantinos Daniel Tsadoridis, and this is a course on the seismic design of structures, in particular steel and steel concrete composite structures. I hope you enjoy it. I will start this presentation by revising and refreshing all these concepts that we've learned the past few days about the seismic design of structures, and of course bring them again, refresh them, and connect them with the steel structures. The same concepts apply. So the most important thing for steel is its ductility demand. Steel is a ductile material, so starting with that, we can clearly say that steel structures do behave well in seismic zones. Plastic hinge formation, as you have already told, is what we are looking at in order to dissipate the energy required. So there are dissipative and non-dissipative structures, and we need to be able to distinguish those. When we design the structures, we're following the proportioning, and we have a proportioned design in order to make sure which elements will be the ductile ones to dissipate the energy and which elements they will behave elastically. The overstrength factors, as you have used for the concrete, will be using the same similar factors with the same concept for the steel. And one of the most important concepts for the steel structures in seismic engineering is the strong column weak beam concept, which is mainly related to the joints, so is including the beams as well. And what we're trying to do is to make sure that the columns remain intact and all the plasticity is actually moved in the column, so in the beam, sorry. So the beam is the one that behaves inelastically. With that, the fuse concept has been one of these that we use quite a lot nowadays. The fuse concept in principle is exactly what we said before, strong column, weak beam, but in steel structures in particular, we have taken it to another level where we are talking about fuses, which, like fuses, they can be removed and replaced. So we're talking about elements that they can be the ductile components, they can dissipate energy, they fail in fact in a controlled manner, and then we can remove them and replace them. And of course, the behavior factor Q for the European codes and the response modification factor R for the American codes is something that I will be using in this presentation, and on some occasions I will compare the European with the American standards so that you have a point of reference and that you can see what are the main differences when we design. Now, why are steel structures good at resisting earthquakes? Steel structures are particularly good at providing an energy dissipation capability due to the following reasons. One is, as we said, the ductility of the steel as a material. Steel is a ductile material, and playing with different grades and different section sizes, we can get the required ductility we want. The many possible ductile mechanisms that we can achieve in steel elements and their connections also give us more freedom in order to design the structure as we like it and to move, let's say, around the ductility point, or the ductility, the damage control, or the plastic hinge where we want. So we have the freedom to locate it in different place, given the different failure mechanisms that we achieve. And the effective duplication of plastic mechanisms at a local level is again part of that. The other thing is that steel is prefab, and it means that it's called reliable geometric properties, so extremely important That's something that we can apply more globally, and we can standardize things, as opposed to what is happening with concrete, which every size of member can be completely different. And lastly, a relatively low sensitivity of the bending resistance of structural elements to the presence of coincident axial force. In the next few slides, we will talk about the importance of ductility, what is encouraged and what is discouraged. Steel structures, by experience, we can tell that those subjected to earthquakes behave well. I know that some people may find it not very true, but overall, because of the ductility performance, as well as the fact that we don't have cracks like what we get in concrete, steel structures are ideal for seismically active zones, and that may be explained by some of the specific features of steel, and of course with that comes the steel concrete composite structures. There are two means by which the earthquake may be resisted. In option 1, we have structures made of sufficiently large sections that they are subject to only elastic stresses. And in option 2, we have structures made of smaller sections designed to form numerous plastic zones. In the past, I would say overall we were designing for option 1. More lately, with the advent of the computational modeling as well, and the more precise design, and of course the overall concept of reducing sizes, we can design with smaller sections and we can control the position and the magnitude of the plastic zones or the plastic hinges. So some examples of dissipative and non-dissipative global behavior of structures. Of course, the non-dissipative ones, it means that it will fail, the structure will fail in a single story mechanism like you see in concept A, where if there is a dissipative structure, then the whole frame will drift. There will be a distributed plasticity over the number of the floors, but it will not collapse. So the structure's global behavior is ductile and corresponds to concept B in the base shear V-top displacement D diagram of this figure. The structure can dissipate a significant amount of energy in these plastic zones, and this energy being represented by the area under the VD curve. So the area is here or there is what it represents the energy dissipated. And for this reason, the two design options are said to lead to dissipative and non-dissipative structures. So you can see the great difference between the two different options that we design for. So this is a good slide, a good picture to have in mind always when you start the design of a steel or steel composite structure for seismic forces. When it comes to the section ductility, what we want is to have a yielding of the entire section and yielding in tension or compression. So this is what it's pretty desirable. What is undesirable is to get local buckling and tensile rupture. Of course, both these mechanisms are going to fail our sections, and we can't control them if you reach at that point, and therefore is undesirable. So in order to achieve the desirable, we need to provide a ductile material, and we have to have highly compact sections with flanges and webs. In order to avoid or eliminate in order to get the undesirable, we have to avoid or eliminate the slender sections, holes, reductions in the cross sections, and I've put these two in italics because there are cases where we can use the holes and other reductions in the cross-section in order to help us with the seismic resistant design, and we'll see a couple of things later on, as well as to configure the weld access holes to avoid local rupture. So again, these are things that we need to avoid or eliminate. When it comes to the member ductility now, we need to provide, again, ductile materials, ductile sections, most probably a lateral bracing system that it will enhance the member ductility. So the member ductility is from the lateral bracing, and connections stronger than members. So the connection doesn't fail, but the member itself can move and can be a ductile member that it bends to a certain degree. What we want to avoid or eliminate is unstable conditions of our members, weak connections, as I just said, as well as weak areas of members. And again, this is pretty much linked with the holes or other openings that we may have in our structure. More importantly, when it comes to the system ductility now, the desirable things are to have large displacement capacities, to have a distributed ductility demands across the whole structure, especially when it comes to along the height of the structure, maintain the lateral resistance at large drifts, and have a damage tolerant design. The undesirable things are the loss of lateral resistance, which we'll see some examples later on and how to avoid that. The excessive member ductility demands, which again, the members have a limited ductility capacity, so if we overload a member and we are seeking for excessive ductility, may fail the member. The instability and the system that cannot tolerate a higher earthquake demand. So these are the system ductilities. And what we need to provide for these is ductile materials, sections, and members, as we said before. Definitely sufficient strength and sufficient stiffness. The system proportioned to spread the yielding across the members of the system. Members that are capable of providing ductility, and members with post-yielding stiffness. So the hardening is extremely important for such structures. We want to avoid or eliminate weak zones, unproportioned overstrength, where one element may be significantly bigger than the other, meaning that this other element will be killed immediately. And members with negative post-yield stiffness we want to avoid. So here we see a classic example, as we saw before, of a non-dissipative structure where we get this interstory, the first story, the soft story mechanism in this particular case, of a concentrated ductility in the first story and the plastic hinges located in the columns. So this is something that definitely we want to avoid. We don't want to have any plasticity in the columns because columns carry the loads of the entire structure, and anything happens on the columns will create huge overturning moments. So we want to avoid that scenario. If we have, though, a distributed ductility, then in most cases we will get the plastic hinges in the beams, and the plastic hinges are positioned near the face of the column, but away enough to get the rotational capacity of the beam without really affecting the connection between the beam and the column itself. By this kind of sketch, you can see the different red dots are of different sizes as well, which is a kind of an indication of the plastic hinge rotational capacity required. So less is required here, of course, much bigger when you go to the lower levels, but if it's distributed, then you will get most of the rotational capacity being in these middle levels, and then there will be the floor, the first level, and then there will be the last levels at the top. So as it says here, the distributed ductility is encouraged by proportioning members, including having similar seismic demand to capacity ratios for all beams. So again, proportioning is the key word here. Now we've got different steel lateral systems. We have the steel moment frames, and these are split in conventional moment frames and special truss moment frames, and we will be looking at the some moment frames in this presentation. And we have the steel braced frames and shear walls. These are again quite standard systems for seismic resistant design. We will not talk much about the shear walls, of course, but the steel braced frames are part of this presentation, and we'll be focusing quite a lot. We have composite moment frames, which are similar to the steel moment frames, but then there is concrete as well, steel concrete composite members, which again, they do change the behavior to a certain degree, and composite braced frames and shear walls. So the presentation here is covering pretty much all these cases, especially when we'll go through the detailed design in the second part of the presentation. There will be reference to all those. So let's start here with the moment frames, the moment frame behavior, some analysis of moment frames, and then talk about the connections and the Northridge lessons. Together with this is the Kobe earthquake, almost the same year happened. The beam to column connection design and construction, and we will end this part of the presentation with some pre-qualified connections. So here we have a typical frame, and we have a lateral seismic force acting on the frame, and you can see here the column shear forces as they are distributed. It appears that the middle columns, they usually have larger forces, shear forces, whereas the end columns, they have usually higher overturning moments. So with the same forces acting on our moment resisting frame, we've got the column moments, which they appear to be higher at the lower stories and of course smaller at the upper stories. And usually the point of contraflecture is at the middle of the column, where is the zero moment, and this is an assumption that we make because this is the ideal scenario. The non-so-ideal scenario is when we have a single curvature of the columns instead of a double curvature, where we will get much higher buckling. We do not want to reach at that point indeed. Here we see the seismic moment on the beams, and as you can see, there is a discontinuity between the moment, which the moment of the beam goes on the column and the moment of the column goes onto the beam. What you see here is just an idealization of the seismic beam moment. This does not include the gravitational and other vertical loads moments. So in that case, when we will design for the total moment applied, we will have to readjust that graph. The most important part of this is that there is this discontinuity at the ends of the beams with the moments applied on the system. And wherever there is moment, there is shear, and wherever there is shear, there is moment. So here we see the beam shear that is coming again from the lateral seismic forces. And again, it appears that the ones in the middle usually they have a higher shear, whereas the ends, the shear of the members is lower, and of course it's lower as we go to the higher floors as well. And here we see the overturning moments, the total overturning moments on the columns. It's usually the case that the overturning moments are higher in the end columns and 0 in the internal columns. There might be the case that we've got some overturning moments in the interior columns if there is a difference of the beam shears. So if it's unequal beam shears, you will get some overturning moments in the internal columns as well. But what we are designing for predominantly is for the end columns. So all the slides that I've just shown, they are assuming that we are working on the centerline model. So the bending moment looks like this. But in reality, there are member depths, and that will change a lot the profile of the moments. In fact, if you look at what's happening here is that the beam stops short of the center lines, and the moment on the beam it stops at the flange of the column, and equally the moment of the column it stops at the end of the beam. In fact, the theoretical values that we have calculated are higher than the actual values we will have in our design because of considering the depths of the section. So equally here there is a zone where is the moment reversal in columns at the connection at this point where we've got this different profile than the one that we're considering at 0 level between the connection of the beam to the column. And equally there is a high moment gradient in column at the connection, and that needs to be considered. So when we do the design, we have to be careful and have in mind that the actual moment profiles as well as the shear profiles are not the ones that we calculate when we have centerline models, but when we have the actual sections which will change the profiles themselves. Same thing appears when we have the model for the shear detail. As you can see on the left is the centerline model, but when we have the member depths, the profile of the shear changes. So we've got the beam stop short of center lines, we've got the shear reversal in columns at the connection, so you can see now that the shear is on the left, whereas the column, let's just show you here. So you see here that although this is on the right, this is on the left. So at the beam's depth, we've got a high shear in the column. And this particular one, because it is quite high, is significantly higher than the shear we get in the columns, in the rest of the columns, is called the panel shear zone. So in seismic design of steel structures, we will focus a lot about the shear panel zone, which is exactly this area, is the area that its height is equal to the depth of the beam, and of course is part of the column. So the last slide before I move on to the braced frame systems is the fuse concept, as we kind of mentioned before. The fuse is the part where we will get this required ductility in order to distribute the ductility and dissipate some energy. So the fuse part is the one we want to not to be over strength, so we don't want to have a very high rotational capacity, but also strength, which will then move the problem to other areas, other elements of the system, so we may get yielding in other components before the position of the fuse. So the fuse concept, it has to be well proportioned in the design. So we need to derive the seismic forces from the beam hinges, and we do that by first sizing our members for a stiff enough frame, and then we calculate the plastic moment capacity of the beam, the MPLRD, and from that we derive the forces that correspond to that, and the shear that corresponds to the formation of the plastic hinges. We then make sure that the beam is governed by flexure and not shear, especially for the moment resisting frames, as well as we'll see later on for those that use the RBS connections. We definitely want them to be governed by flexure. And also we derive other forces in the columns, such as the shear and the flexure. For the column axial force is derived by the estimated proportioning of the beam, and the beam flexural capacity is used in order to get the panel zone shear, as we saw before. Alright, so here we'll start with the braced frame systems. To begin with, we have the ordinary concentrically braced frame, and this is limited by the inelastic drift demand through strength. Here we're talking about strong braced frames that they have a low R factor or Q factor, and they are predominantly used for warehouse buildings or low buildings to mid-rise in seismic active zones, predominantly for low-rise buildings. So we are here talking about buildings that they don't have much inelastic capacity. Then is the concentrically braced frames, and these are special concentrically braced frames that they have an inelastic drift, and they can achieve that through buckling and yielding of the braces, as we can see here, either in compression or in tension. These are usually designed for high-rise buildings in seismic active zones. Lastly, we have the buckling restrained braced frames. These again, they have inelastic drift, which is achieved through yielding of the brace. In these particular systems, we have a very detailed BRB diagonal member, which can yield in both compression and tension, so in a ductile manner. So these are of course more expensive, but they have the capacity of large inelastic drifts. Again, when we design those, we have to limit the inelastic drift at a certain degree, which beyond that, the BRB will not be of any use anymore. Next is an eccentric braced frame. One of the eccentric braced frames is the one we see here. And in this case, we don't have braces intersecting anymore, so they never intersect. And there is a zone in the middle, which is called the link zone. This is in fact a steel beam, which has some inelastic drift. So the inelastic drift capacity of the system is based on the yielding of the link and the shear or the moment that this link beam is experiencing. This link can be subjected in shear, moment, or both of the two, and it is a ductile member. So it is a very ductile member, in fact, excuse me, and the inelastic drift capacity is based on the ductility of that member itself. To quickly synopsize this, concentrically braced frames, we encourage the yielding of the braces or the buckling of the braces, and these braces, they are acting as fuses. So these are the elements that we want to get the buckling and the yielding in order to make sure that all the other elements, they remain elastic and strong, and they haven't been buckled or yielded. And what we want to avoid is the flexural hinging in columns that will create a story mechanism. We've explained that earlier. The buckling of beams or columns, of course, as you can see in the second picture, and the connection failure, which will inevitably break the bracing system, and therefore the inelastic forces will be moved to the columns. For the eccentrically braced frames, we encourage the yielding of the link. Again, this link is now our fuse, and we want to avoid the flexural hinging in columns, the story mechanism. And you can see here 3 different ways of having, for instance, a link which is not very ductile, and the plastic hinges will be formed in the columns, or a link which is ductile, but then the column also gets some buckling, so the column is not strong enough. Again, think about the proportioned design. And the last one is, again, when the connections are failing, where everything will be moved in the columns. Next is a system that we haven't seen too much being used, especially in Europe, but it has been used in other countries, and this is the steel plate shear walls. There is more and more research, experimental and computational, that is coming up with this. I must say that I'm also working quite a lot on steel plate shear walls, and that's an interesting system, in fact. So it's sort of like an infill wall of a steel plate with perforations or without, and that is providing some inelastic capacity, and we're expecting that the plates will yield at some point to dissipate that energy and provide the ductility, the required ductility. So we will then get the flexural yielding of beams, and as you can see here, the plastic hinges are on beams. So the fuses in this system is both the beams at this, where we'll get the plastic hinges, as well as the plate itself that it will buckle. What we want to avoid here is the flexural hinging, again, in columns, to avoid any sort of story mechanism, as well as the buckling of beams and of columns and beams. So again, the design of the SPSW has to be proportioned, so that the ductility is achieved before we've reached the capacity of the other members that we want them to remain elastic, like the beams and especially the columns. All right, so let's now move to the special concentrically braced frames, SCBF, and see exactly what kind of forces we've got there, what we want and what we want to avoid, and see some unfavorable modes of failure as well. So first of all, we want the inelastic drift through the brace axial ductility. So this is the capacity of the bracing to contract and elongate axially. And that is achieved by tension yielding in the bracing and compression buckling in the bracing. So seismic load is a reversible load, so it goes back and forth. So the same member will be subjected to both tension and compression buckling. And these two, although they are opposite in the sense of the form of the load, the direction of the load, they're not just opposite in terms of what is really happening there, because tension is a distributed strain along the member, whereas compression buckling is in fact a flexural buckling that is happening in the member. So that is defined by the EI of the member, but that is followed by a local buckling, which is the plastic hinge formation in the member. So the mode of failure is quite different. So in terms of design, when the braces are sized for compression mainly, and this is because the compression capacity is lower than the tension capacity of the braces. There is a high overstrength due to tension capacity. Of course, you can imagine that if you design for compression and that is high, the tensile capacity will be even higher of that. When it comes to the frame resistance, the frame itself is defined by the brace tension strength. So the capacity of the frame is much higher. The braces must survive buckling and maintain tension. So what we want to achieve, in fact, is to get the buckling of the braces, but that buckling does not reduce the tensile capacity of the members when the load is reversed and now the braces are in tension. So in fact, although the braces will be compressed, they will be loaded in compression, and they will form a plastic hinge. In fact, what we don't want is to get to an instability point where the system will be not stable any further, and it will create the failure of that. That will lead to the failure of that member. But if the plastic hinge is formed in a controlled manner, then that's absolutely fine. In the reversed load, the same member will be subjected in tension, and if the tensile capacity is not really affected by its previous state being in compression, then we have a perfect design. So frame members designed for maximum braced forces, of course, and that prevents unfavorable modes of failure, as we'll see in the next few slides. So first, a few of the modes that we don't want to get. First one is the connection failure. When there is no enough inelastic capacity and ductility of the bracing member, we may get a connection failure, and that will then lead to high inelastic behavior of the column. So this is something that we want to avoid, and in order to protect that, we need to make sure that the connection is strong enough. When the load is reversed, we have now the bracing in compression, and what we want to make sure is that we will not get a column buckling, so the column is stronger than the buckling member, and the buckling member will have the required ductility to buckle the bracing. So in that case, of course, this is a very severe failure mode, because in most cases the column will not come back to its initial position, meaning that it will cause huge overturning moments on the column and most probably the collapse of the frame of the structure. We also need to protect our structure from column tension fracture, which means that we design the splices and the base plates for the maximum capacity of the bracing members, so that we do not really get any failure of these before the bracing member buckles. In this case, it's not too often that is happening, but we never know if that frame returns back to its initial position, whether we'll be able to withstand the gravitational forces and the reaction of that. So again, we want to avoid this type of failure mode, and less likely to get any beam fracture. But again, the beam failure must not limit the design, and that's why the beams should be not behaving elastically. They should behave inelastically. They should behave elastically. Now, some of the preferred modes, one of these is the brace tension yielding. So if we get enough elongation, we will get the yielding of the bracing member, and in case that the gusset plates and the connections do not fail, this is a favorable behavior. We consider that there is no strain hardening after the Fy is reached, which is not the case. In reality there is, but for simplification we assume there is no. So we are considering the maximum effect due to the brace force. And a little bit more complicated is when the brace is buckling with a reverse load. Now we have, in fact, a steel degradation. So what's happening is at the beginning, the bracing buckles and it reaches its maximum buckling capacity. But as the load goes back and forth, it reverses to the tension and then compression again. The capacity of the bracing now has been reduced in compression to approximately, after several cycles, to 30%. So we consider that the maximum effects due to brace are sometimes about the 30% reduced. As you can see on the graph on the right, that is represented that at large displacements we have a reduced buckling capacity of the bracing member. And here we can see a nice picture of an experimental setup. So this is the frame laid horizontally. This is just part of the a reaction frame, the testing frame. It has been painted in white in order to be able to observe clearly where the buckling has taken place, and after one or two cycles we can see that there is a local buckling of the bracing member. The thicker is this section here. It means that it will be able to withstand that sort of buckling, and then it will come back in tension and then buckle again. If it's very thin, most probably it will break and will fracture, and then the inelastic forces will move to other members of the frame, such as beams and columns, something that we do not want to achieve. So another aspect of the behavior of the braced frames is that we may get an non-equally distributed force along the height of that braced frame. We tend to think that a braced frame is a vertical bracing, is a vertical cantilever, and everything moves in one way, but in fact we do get a different sort of modes of failure. So in this case here we get a column flexural because of the first story buckle bracing that buckles. So you see this one is buckling, and because of that we get that column which bends. So this is something that again we need to consider when we proportioning and we design all our components, the beams, the columns, the cassette plates, or any kind of connections in comparison to the design of the bracing. Equally, you may have another type of bracing like this one, and in this case the bracing here is in compression, so it buckles and it drags down the beam, so there is a yielding flexural bending of the beam because of the bracing which is buckling. So again, this is changing the mode of failure for the entire system. So again, these things need to be considered, and do not just assume that the bracing will do the entire job. Locally will buckle and there will be a plastic hinge here, and there's not going to be any other plastic hinge in the beams and columns, and everything will be evenly distributed along the heights of the system. Just to put things in perspective, in the top case we have a bracing which has two directions, and in this case we will get a behavior which is very symmetric. Nothing makes this asymmetric. Even if we have a different compression and tension capacity of the braces, these two braces, they will act as symmetric, and with the degradation over subsequent cycles, yet this makes a very kind of symmetric hysteretic behavior. However, if we have a bracing like this in one direction only, then what's happening is that in one direction we have quite high strength, whereas in the opposite direction the strength is very low. So we would expect that this high strength here, if we reach at that point here, we will have a remaining elastic strain, which will be enough in certain cases to reach the inelastic capacity of the bracing on the opposite direction. So that said, this is a not good, it is a bad design for a bracing, and in most cases we're trying to avoid something like that, but we go for a symmetric bracing. Let's now look at some details of experimental projects. Here we see a buckling of the bracing. The reason I'm having this slide here is just to show that there is significant buckling of the bracing, and from that perspective we cannot see anything happening on the gusset plate, which is a good design. If we look at from another perspective, we see that the gusset plate has also deformed because of the buckling that the bracing is experiencing. This is a good design. In fact, you will get some sort of bending and deformation even if you have a thick gusset plate. However, that is not failing, so the bracing, it has done its job by buckling, so it has already moved in a ductile manner. Here we see the three different recommended ways of designing the gusset plates as they come from the American design seismic codes, the ISC design codes. On the first case on the left, we see a typical gusset plate and the brace connected to it. This line here represents the position of the plastic hinge, and of course what's important here is to make sure that the width of that is adequate to withstand the inelastic forces and form the plastic hinge. In the second scenario, there is a knife plate that is used with a gusset plate, and here there is a gap between the gusset plate and the brace, and this gap is where we are anticipating to get the plastic hinge. And again, the formulae are telling us what should be that distance here between the gusset plate and the brace. And I believe some tests have been done in Taiwan. For this third option, which is a bit more complicated, Washington University has done some experimental work, and this is a kind of an elliptical here formation of the plastic hinge. So there are some trigonometric rules that they are telling us exactly where that plastic hinge will take place. The gusset plate here is bigger, as you can see, and it has to be thicker as well because of when the plastic hinge will form near the ends of that plate. It has to be to have the required capacity. And that's why the plate is a bit bigger. However, it allows for more sort of like freedom in this case. Therefore, we can get more ductility from the bracing member connected to such a system. Here we see a fixed end brace connection, how it looks like. We have the bracing member and two plates being welded to the bracing member. So the bracing member here, this connection is quite strong. So we expect that the bracing will fail. And again, like before, we are not going to get any sort of bending of the plates. It's going to be only some deformation in the elastic region. So when that returns, you will not be able to see anything on those plates. Now, just a quick couple of pictures on the BRB types. There are several BRB types, as you can see here. So, unfortunately, we don't have the time to go through the BRB design and just the to see the anatomy and how it looks like inside. But even if you use BRBs, you will see that the connection to the frame is pretty similar. We may use some like double angle sections with bolts, or a thick gusset plate with a pin to allow for the movement of the BRB system. Again, here, like before, gusset plate and fin plates with bolts or rivets. And in fact, what I wanted to show here is that the system design for the detailing is not much different to what it is for a standard brace system. Connections can fail in many different modes, so it's quite complicated, and there is a lot of work that needs to be done to make sure that connections won't fail before we get all the inelastic capacity we want and ductility from the brace members. There is a quick sort of way of designing gusset plates, like this rule from Doswell, that it says if the thickness of the gusset plate is bigger than this parameter, T beta, then it's safe and you will not get any failure of the gusset plate. So in this parameter you can see the distance C and the LB, and of course Fy and Young's modulus. So a quick way to calculate, to design a gusset plate. So we have a number of failure mechanisms that we have to design for. We have the column web yielding and column web crippling in the zone where the gusset plate is. We have the column web shear, as we've seen before, the beam web yielding, crippling, and shear in this zone, and of course the beam to column connection shear, and the beam column connection axial force that we need to design for. Now, in the connection fixity problem, we have to be quite careful, because we will either design our connections to be as simple, and we will then design for ductility, or we will design them as rigid, and we will then design for strength for capacity. So we have to make sure that we go to one or the other way, because here we see the moment rotation behavior of the connections. In seismic design, we either design as a fully rigid connection or as a simple connection. So if you design as a rigid connection, then you design for strength, so the connection should have a sufficient strength. If you design for as a simple connection, then you design for rotation. Now, when you have a simple connection like this and you add a gusset plate with a brace, then you must appreciate that the behavior of the connection is changing. The stiffness is higher, the capacity is though lower than what it is for a fully rigid connection, and of course there is an increased ductility and rotational capacity, and that is something that most cases we don't know how much it is for our connection. So it's best to work with the fabricator of the connection, test the connection, and find out what is the actual ductility performance. Essentially, there are three alternative methods of connecting and doing the design, the calculations. One is when we have the beam capacity that is divided by two coupled forces, and these will increase the demand of what's happening here, and of course it will increase the demand of what's happening here between the column and the gusset plate. So the connection strength exceeds the beam strength in this kind of scenario. The other is to just account for a rigid connection in which the moments are implicitly, not explicitly, accounted for. So we just account for the moments of the beam and we add the capacity that we have from this system. So we don't really design for that. We just say that as long as this is fine, the added capacity will also be fine. So this is a simpler form of what we've got here in terms of doing the calculations. And the last one is a flexible connection where rotations are accommodated. So we use a single plate here and we have a moment on the beam. And what we are expecting is that this beam here will rotate. So we are accounting for about 2.5% rotation capacity. Easily we can achieve that, if not more than that, by such a connection. And finally, when it comes to the design of the base plates, both shear and tension are accounted for. So the resistance to horizontal and vertical forces must be provided, and different mechanisms can be used for that. So as we saw previously in one of the experimental pictures, it's relatively straightforward to connect the gusset plate through the base plate and the foundation design. Here we see a quick synopsis of the steel dissipative mechanisms, and We, as a designers, we're trying to find all these components that they can dissipate energy, and we need to know which ones they cannot. So on this picture, I'm sorry that it doesn't look very clear. You can see the local mechanisms, the dissipative on the left and non-dissipative on the right. So what sort of failure modes we want to get when it comes to the compression or tension yielding of the members, and how the members they should move. For instance, beams failing in yielding in shear, or they creating these plastic mechanisms. All these things are what we need to observe when we do our analysis to make sure that we have enough inelastic capacity and ductility in certain components that will dissipate our energy. Other important factors that we need to consider is the variety and reliability of possible energy dissipation mechanisms in steel structures, is the guaranteed material strength as a result of the controlled production, the designs and construction carried out by experienced personnel, flexibility and low weight of the structure, which will cause a less earthquake impact on your structure. So reducing the masses, reducing the weights inevitably will lead to lower seismic design forces, and the reduction in the cost of both the superstructure and the foundations of a building. So again, it is a proportion designed. We should not over design our structure, and we should keep the balances between the design of the components and the members of the structure. Alright, so this is the second part of the presentation, and here we will talk about the design provisions and how the Eurocode 8 is treating the seismic design of steel and composite structures. To start with, we have the European recommendation for steel structures in seismic zones by the ECCS group, and a very good book that I recommend for the design manual with some very nice design examples. The Eurocode 8 section 6 is the one that is dealing with steel buildings. Here is a synopsis of the contents of that section. You can see that Section 1 is the general information for the concept and safety verification. 6.2 is the materials and the steel properties. 6.3 is different structural types and behavior factors, and that's kind of like empirical formulas, empirical values. 6.4, the structural analysis with the design criteria and detailing rules. 6.5, and then this part is the ductility requirements overall with the rules for dissipative members and connections, whereas the last part of 6.6 to 6.10 is the rules for global hierarchy and global capacity design for specified dissipative structural types. And as you can see, there is some detailing rules for moment resisting frames, concentric and eccentric braces, as we discussed before. The inverted pendulum structures, which we haven't discussed much, but this is the simplest concept. And some design rules for concentric braces, combined concentric braces and infills, as we saw before in one slide very briefly. So the first thing that the designer has to do is to classify the structure in terms of ductility. So at the beginning, you have to choose whether this structure will be designed as a non-dissipative structure as usual, or it will be designed as a dissipative structure. All seismic codes leave the choice between these two concepts open and define several ductility classes. So it's up to you to decide which one you want to go for, mainly given on the land conditions, the geotechnical conditions, whether it's an area of the high seismicity or not. In Eurocode 8, there are 3 ductility classes defined, starting with the DSL, which is the low ductility for non-dissipative structures, the DCM, which is the medium ductility, and the DCH, which is the high ductility. So just look at the last letter for low, medium, and high ductility. So designing a structure to be class DCL means taking into consideration the highest design forces, but only performing the usual static design checks. For example, using the Eurocode 3 or using the Eurocode 4 if you're doing steel concrete composite. Designing for high ductility, then it means that we are designing for the highest possible behavior factor Q, and this approach results in the smallest possible design earthquake actions and seismic action effects. So bending moments, etc. are reduced, but not the displacements in particular. So for high ductility, we are reducing the capacity of the structure, so we are designing for lower capacity in order to accommodate the ductility and get first the ductile behavior of certain members and connections, as we discussed before, in prior of reaching the capacity of the structure. So here is a synopsis of the design concepts. On the left we have non-dissipative and dissipative structural behaviors. We have different classes, low ductility, medium ductility, and high ductility. And there is a reference here of the behavior factor Q and what should be the required cross-sectional class for these dissipative elements. So as you see, for the non-dissipative low ductility structures, the Q is quite small. It should be smaller than 1.5, whereas when we go to high ductility classes, then the Q is also getting higher. Of course, for high ductility classes, we want to use a class 1 section, a kind of a compact section that it will not fail, it will not break easily, and it will not be unstable itself. Whereas when it comes to non-dissipative structures, very strong structures that they don't have any ductility capacity, then we can design for class 1, 2, or 3. Of course, class 4 is not considered at all. So going to the design criteria for low dissipative structures, the structures with low dissipative behavior can be designed according to DCL concept as described in Eurocode 8. The strength assigned to the structure is sufficiently large to make the plastic deformation demand from the design earthquake sufficiently small, and some detailing rules for ductility can be waived. In other words, these structures are designed for strength, and the ductility performance and the plastic deformation is relatively small. There is a large uncertainty about the seismic actions, and there is a chance that the intensity of a real earthquake will exceed the design value in such cases. Hence, the demand will be larger than assumed for the design. In other words, we will over-design the structure, we will provide more strength to the structure to account for the uncertainty of larger seismic actions onto that structure. In other words, the low dissipative concept should be used with caution. Eurocode 8 suggests only in cases in low seismicity zone. So because of this uncertainty and because of the fact that we're not really using the ductility of the structure, then we should be cautious with how much we over design and in what kind of structure we use it. I would say low seismicity zone and really low height structures. When it comes to design criteria for dissipative structures, now these shall be designed such that yielding or local buckling or other phenomena due to hysteretic behavior do not affect the overall stability of the structure. That's extremely important. We will get yielding and we will get local buckling, but we need to make sure that these will not create an instability on the structure. And this is exactly what I was explaining in my previous slides in session 1 of this course. The dissipative zones shall have adequate ductility and resistance, and the resistance shall be verified in accordance with Eurocode 3. Dissipative zones may be located in the structural members or in the connections, as we saw before, ideally in some brace members, otherwise they will go to beams, and or in the connections so long they are designed for that. If dissipative zones are located in the structural members, the non-dissipative parts and the connections of the dissipative parts of the structure shall have sufficient overstrength to allow the development of cyclic yielding in the dissipative parts. And the vice versa, when dissipative zones are located in the connections, the connected members to those connections shall have sufficient overstrength to allow the development of the cyclic yielding in the connections. So in other words, we are again talking about the proportioned design and understanding how to balance out the sizes when you design your structure, whether you want it to have a dissipative structural member being the brace or the beam, or to be the connection. Accordingly, then you will design the members connected to that connection. When it comes to the material properties, the dissipative zones have to be made of a ductile material. I think now everybody appreciates that. If correct structural steel grades are used, then the material elongation, especially of members such as braces, will be over 15%, and the ductility defined as epsilon y max over epsilon y will be over 15. So we're talking about a distributed strain and an elongation of the element that can reach up to that percentage. The adequacy of the steel is related to the properties needed to achieve the ductility of the structural elements, and that's a need for high elongation that requires the F ultimate over the Fy being greater than 1.1. Other requirements are the correct toughness at working temperature, and you can see a reference here. And in addition to the steel itself, the weld materials and bolts must also be adequate. And again, you can go back to the slide, one of the last slides of the previous session, where I was showing the dissipative and non-dissipative components of the connections and see which ones we have to design for what. So the recent studies have shown that Eurocode 8 rules are quite on the safe side, quite conservative, especially when they were direct comparisons between the Eurocode 8 and the American codes. We can see that the Eurocode 8 is somewhat more conservative. Here is the formula for estimating the actual yield strength of dissipative members and connections, which can be substantially larger than the nominal one. So the Fy max is smaller or equal to 1.1 times the recommended overstrength factor from Eurocode 8, and that is 1.25 times the yield strength. Before we go to the behavior factors and how these are presented by Eurocode 8, let's again synopsize the structural types. We have the moment resisting frames, that they are resisting the horizontal forces by essentially getting a flexural flexure on the members. We have the concentric braces, in which we have axial forces in the members, tension and compression, as we discussed before. We have the eccentric braces, and we mainly focused on the seismic links by getting the cyclic bending or cyclic shear of that link element. And we have the inverted pendulum structures, which are located at the bases of columns, and we haven't discussed that much. Is unfortunately one of the things that we did not have time to go through. And we have the structures with concrete cores or concrete walls, and again the cores and the walls are resisting the lateral forces. So the code behavior factors are mostly empirical and are supposed to account for the ductility, redundancy, and overstrength of these different structural typologies. So here is the table where it presents the systems we just mentioned and the low, medium, and high ductility classes, and as you can see, there are different numbers which are given for different cases, but overall we can say that the low ductility, we're talking about a behavior factor Q of 1.5, and there is the number 2 in the asterisk, which says that the national annex can allow for Q equal 2 in class DCL. So have a look at that when you are working here in the UK. We have the DCM, which is 4 or 2 depending on whether it is a moment resisting frame, a concentric braced frame, or number 2 is when you have an inverted pendulum or you have concrete or infill walls. And then we have for high ductility classes either a number or a number times this ratio, which we will explain in the next slide. So this plastic redistribution parameter is the ratio of A alpha U over alpha 1. The parameter alpha 1 is the multiplier of the horizontal seismic design action needed to reach the plastic resistance in one part of the structure. Alpha U is the multiplier of the horizontal seismic design action needed to form a global mechanism. So we're talking about the multiplier for the global mechanism over the multiplier for getting the plastic resistance in one part of the structure. So the ratio may be obtained from the nonlinear static pushover analysis, but is limited to 1.6. The values for the ratio are taken from Eurocode 8, and you can see here that for different types of structures, different typologies, we have different parameters. For instance, on the top left, we have, let me just find the mouse, we have a warehouse building, and that is 1.1. As we go to higher buildings, that is increasing. When you have more base, again, that factor, the plastic distribution, is increasing. Again, reminding you that we cannot go to anything more than 1.6. For braced frames, concentric and eccentric, we have a plastic distribution parameter equals to 1.2. Table 5.1, it synopsizes very nicely the behavior factors in European as well as the US provisions. So you can see here the Q factor for the top half of the table and the R factor, which is the same thing as I have explained in slide 2 of the first session. For the US provisions, of course, for each different typology of structural typology, we have different Q factor. Again, these are empirical. These are based on certain research studies that we have done, but these may change in the future. It doesn't mean that the factor is 100% accurate. Of course, the higher the factor is, the more the ductility that is provided in the structure. The lower the factor is, the less the ductility. That's why the non-dissipative ones, they get like 1.1. Now, in the US, that's, I think, one of the biggest differences is that the non-dissipative ones, they are designed for a Q factor equals 3. And as you can see, the factors, they are getting much higher overall. But of course, we're talking about a different seismicity zones. A general concept when we design dissipative structures for seismic forces is to have a primary structure and a secondary structure. The vertical load resisting structure may comprise a main or a primary system designed to carry the total earthquake effects, and a secondary one which is designed to carry only the gravity loads. The physical reality of the frame must reflect this distinction, and the contribution to lateral stiffness and resistance of the secondary structure should not exceed the 15% of that of the primary structure. So it is appropriate to design for this distinction of the primary and the secondary structure. The members of the secondary structure and their connections must be able to accommodate the displacements of the primary structure, responding to an earthquake while remaining capable of carrying, of course, the gravitational loads. So in a quick schematic representation, this is what we need. We need a primary structure, which can be a strong frame in the middle, a braced frame or something else, and then we have the secondary structure, which is all around of that. A good conceptual design will enable a structural system to resist earthquakes that has low additional costs compared to a non-seismic design, and that's extremely important. We should not over-design our structure because of the seismic loads that we've got. The primary resisting system allows much more architectural freedom in the design of the secondary structure, which may be the more important for the exterior aspects of the building. So have these in your mind when you are designing a seismic resistant steel structure, that you need to distinguish the primary and the secondary one. Now I will go through the design based on the selection of the ductility class. So at the start, as we said before, the designer is free to choose the ductility class. If a low dissipative structure is designed, we just need to follow the basic design codes. The seismic code defines the seismic action, and the behavior factor is minimal, so the Q is equal to 1.5. The requirements on the materials and classes of the section are minor, and no checks from the seismic code need to be applied, with some eventual minor local plastic zones that we may get. When we are considering ductility classes medium and high, then the Q factor is ranging from 2 to 6. Here is very important that the weight of the structural elements can be substantially reduced, although the design process itself is more onerous, and there are restrictions on the classes of sections, on the connections, on the materials, and on the control of the material properties. With regards to this reduction of the weights, we usually try to reduce the weight so that we have a smaller effect of the seismic forces on the structure, and in this way we will be able to reach the ductility, but we're not going to reach the strength of the structure. So we'll design for ductility purposes. Designing a dissipative structure normally results in a more competitive solution. It's more complex. However, this is not always the case because of the seismic checks may not be critical. There are limitations of the beam deflection under gravity loading may govern the size of the sections needed, and capacity design results in dissipative sections which have higher overstrength, which then leads to overall overstrength. And indeed, the limitation of the beam deflections is usually what it defines, governs the design. This situation is more likely to occur in areas of low seismicity and for flexible structures for which the SLS can be the most important. Of course, when we're talking about high seismicity, then we're not really looking at the SLS and the deflection of the beams, but the ductility of the members. Hence, it can be concluded qualitatively that the high dissipative solutions would in general be best in zones of high seismic activity, while the medium and low would be most appropriate for medium and low zones respectively. And I guess this is why they call them like that. The choice of a ductility class for a given design also depends on the mass over volume ratio of the structure. If the structure is essentially empty, for instance, we're talking about an industrial building, the wind resultant force can be greater than the design base shear determined with the behavior factor of a non-dissipative structure. So it's a Q equals to 1.5. So designing for high ductility is of no interest, is no good. Conversely, if a structure is of high mass and stiff, a high or medium ductility design can be the best option, even if in areas of low seismicity. So I think that's a very good analogy to have in yourself based on how heavy it's your structure. A very heavy structure, even in low seismicity zones, better be designed for a higher Q, for a high and medium dissipative, whereas a low rise structure, especially if it's empty, if there is a lot of volume inside, it better be designed even in seismic zones with a behavioral factor of 1.5. Now, while selecting a type of the structure for the design, we need to make sure that we are choosing the most cost-effective solution, because at the end of the day, pretty much all types of structures can be designed to resist earthquakes. So starting with the moment-resisting frames, usually these are governed by deformations. This generally results in the significant overstrength in order to avoid having deformations. One way to avoid this situation is to consist of designing to stiff facade frame as the primary structure in the perimeter of the building, while the interior frames are secondary structures and they are carrying the gravitational loads. And this is pretty often, especially for high-rise buildings, we see that a lot. When it comes to concentric bracing, these are stiff by nature anyway, but their behavior factors Q are not the highest possible. So we need to add something to it to increase the Q factor and reduce the weight of the structure, the over-design of the structure. Frames with eccentric bracing is they combine the high energy dissipation capacity and the behavior factors Q associated with the moment resisting frames with a stiffness that is similar to that of the frames with the concentric bracing. And frames with bracing are rather invasive, as the bracing may interfere, it cuts into the free space, so they should be placed around the periphery of the building as stiff primary structures to resist the earthquakes, while the interior secondary structures carry the gravity loading. I think that's pretty much the only solution when we have frames with braces. Otherwise they will interrupt the interior architectural design of the building. Let's go now through the common rules for dissipative structures quite briefly. Elements in compression, sufficient ductility of members which dissipate energy in compression or bending shall be ensured by restricting the width to thickness ratios, like we do in Eurocode 3. So some differences appear in the US and the Eurocode 8 values for hollow sections, and we can see on the bottom right the graph that it shows kind of certain differences that we may have. For elements in tension or parts of members in tension, the ductility requirement again of Eurocode 3 should be met. Where capacity design is requested, the design plastic resistance should be less than the design ultimate resistance. So the NPLRD should be smaller than the NURD. Therefore, the A of the net resistant area over the gross area should be bigger or equal to that parameter 1.1 times the ratio. For connections, we discussed this before. We said that the dissipative zones may be located in the structural members or in the connection, depending on which one you are over strengthening the other. So if the dissipative, the plastic hinge will happen in the connection, then the members connected to these should be over strengthened and vice versa. So on the right, we can see on the top the design, the option design, where the plastic hinge has formed in the beam. So the horizontal member here is in fact the column, and here's the beam with the end plate and bolted extended end plate, and the plastic hinge is formed in the beam, whereas in this design the plastic hinge has been formed in the end plate. So it's part of the connection where the beam is over strengthened. So you can even see here that the beam in fact is deeper than the section of the column. When we have non-dissipative connections, the design rule for rigid full strength connections is common to all types of structures, and the resistance RD of the non-dissipative connection should satisfy the following formula. As we saw before, RD is greater or equal to 1.1 times the overstrength factor times the plastic resistance of the connected dissipative members. The rule applies to non-dissipative connections using fillet welds or bolts, and when full penetration butt welds are used, they automatically satisfy the capacity design criterion. Coming to dissipative connections, of course, we're looking at here the hysteretic, the cyclic performance of the connections. Eurocode 8 allows the formation of plastic hinges in the connections in the case of partial strength and or semi-rigid joints, provided that the joint cyclic rotation capacity should be at least as 35 mrads in case of the high ductility, high dissipative capacity, or 25 mrad in case of medium capacity. So as I said before, in the connections that they are having at least 25% rotational capacity, those are the medium ones, so we can even go for higher. In Eurocode 8 it does go to higher demands of rotational capacity as well. So this is a very typical representation of different joints and their hysteretic performance. Of course, with having different parts of the connection, if you add braces or haunches, if you have a different bolted connection, or if you have an RBS or RWS system, as we will see later on, these hysteretic performances are changing quite a lot, but this is a good representation for your information. So when we have a welded connection, it's a very symmetric as well, and we get this kind of nice and fat cycles, and the degradation is quite small. In most cases, as we've learned from the Kobe-Novgorod earthquakes, we may get a failure of a cracking in the vicinity or on the welding, and there is where we will fail the connection. When we have an end plate joint, then again we can reach high capacity, and in most cases there is a lot of degradation because of the yielding of the bolts. And when we have angle cleat joints, we have even a smaller sort of capacity which has a different profile, and that is very much relevant to the yielding of the angle plates. But as you can see here, there is no much degradation. In fact, there is an increase of the strain that is happening in the connections. So the more they cycle, the higher is the capacity that they go. It is worth to note that the EC8 requires design supported by specific experimental testing in cases where the dissipative connections are newish, and this is resulting in impractical solutions within the typical time and budget constraints of real projects. So there is a need to have already a set of experimental tests for different connections and information tables, tools that come with it in order to be able to use them in a timely fashion in projects. In the US and Japan, there is a list of pre-qualified standard joints which are used, but these cannot be extended, unfortunately, to European standards because of the different materials, section shapes, and welding processes that we've got here. The European pre-qualified steel joints Equal Joints project has just completed a couple of years ago, and that is one of the biggest efforts in the UK to have a number of pre-qualified standard connections, some of them similar to the ones that we have in the US, and some new ones to be checked meticulously and very thoroughly so that they can then be used in Europe immediately without having time implications. And there is also other companies that are producing special joints, such as ArcelorMittal, but I believe there are more of these. I would like to urge at this point the need for doing more work on special connections and pre-qualified standard joints for the European practices, and I would like to urge the companies to support such endeavors. This is a very good table because it synopsizes the R factors and the Q factors, the plastic rotational capacity, and the capacity design of connections and what can be done. So we're looking at here the low ductility, medium ductility, and high ductility, and we have the US and the European kind of standards, like approaches. And of course, we discussed the European ones, which is the low, medium, and high ductility class. And we have the ordinary moment frame, intermediate moment frame, and special moment frames for the US standards. So this table synopsizes the R and Q factor, which is the same thing, and it gives a good recommendation. And together with that, what is the required plastic rotation capacity in MRADs? And you can see that for the low ductility there is no, but for the medium and the high ductility the numbers are ranging from 20 to 40 MRADs. For the capacity design of connections, anything but the low ductility in Europe, the ductility class low, is a yes. Looking a bit more closely at the moment resisting frames, we know that the horizontal forces are mainly resisted by the members acting in flexural manner, and that the energy is dissipated by the means of cyclic bending. So the global mechanism is as we see in the picture. So we have plastic hinges in beams and not in columns. We don't want them to be in columns. The dissipative zones should be mainly located in the plastic hinges in the beams or in the beam to column joints. Again, this is not ideal, but it may be designed accordingly. Dissipative zone in columns may be located at the base of the frame, which is usually the area where we provide a weak point there and we allow for some energy dissipation. You may have seen the base plates floating a little bit higher than the foundation, and that is to allow for the plastic hinge to take place, as well as at the top of the column in the upper story of the multi-story building. In order to allow for the development of the global collapse mechanism, the local capacity design has to be ensured. In frame buildings, the following conditions should be satisfied at all beam to column joints. So the sum of the design values of the moments of the resistance of the columns framing the joint should be greater or equal to 1.3 times the sum of the design values of the moments of resistance of the beams framing that joint. Now, some detailing rules for the moment resisting frame beams. For the plastic hinges in the beams, it should be verified that the full plastic moment resistance and the rotational capacity are not decreased by the compression and shear force. So, like we do for the design of beams when we have increased shear in Eurocode 3, the same concept applies here. So at the location of the expected plastic hinge, it should be verified that the applied moment over the plastic moment resistance is equal or is lower or equal to 1. At that position, the applied axial load over the axial plastic resistance is smaller or equal to 0.15. So the resistance now, it has to be quite significant. And the design value of the shear force due to the non-seismic forces plus the design value of the shear force due to the two plastic moments that are formed within the same sign at the location of the plastic hinges over the plastic moment resistance, the shear plastic resistance should be smaller or equal to 0.5. And for more information, we have here the beam with the moments. We've got the moments due to the gravity forces and the moment due to the seismic forces, and the combined moment of the two, which is the MED. And we have the before and after redistribution of the moment graph as well. And at the bottom we see the shear, the seismic shear forces applied. So now coming to the columns shall be verified considering the most unfavorable combination of the axial force and the bending moment, assuming the following rules. The NED is equal to the NED of the gravitational loads plus 1.1 times the overstrength factor times omega, which is the minimum value of the MPLRD over MEI of all beams in which dissipative zones are located, times the NED E, which is the design value of the effects of the seismic actions. For the MED is the same thing, so MED is equal to the MEDG for the non-seismic actions plus 1.1 times the overstrength factor times omega times MEDE. And for the VED, again, the same design value and design formula as before. The column shear force shall satisfy the relation of the VED over VPLRD smaller or equal to 0.5. So that rule that comes from Eurocode 3, it applies here as well. We don't want to get the reduced moment capacity because of high shear in the beams and the columns. When it comes to beam-column connections, now if the structure is designed to dissipate energy in the beams, the beam-to-column connections of the whole frame must provide adequate overstrength to permit the formation of the plastic hinges at the end of the beams, as we already said it a couple of times. So the following relation must be achieved. So we have the MJ, which is the bending moment resistance of the connection, of the joint, in fact. That should be again greater or equal to 1.1 times the overstrength factor times the MBPLRD, which is the bending moment resistance of the connected beam. So as you can see, the formula of 1.1 times the overstrength factor, it does apply to all the checks that we do. When it comes to the detailed design of a rigid beam to column connection, there are basically three different approaches. One is to use a classical connection design. In these cases, probably the plastic hinge will be formed in the beam section adjacent to the column flange. So somewhere here, either before or after the plate, most probably after that plate is where we will get the plastic hinge. Another option is to use other elements, cover plates, brackets, and move the position of the plastic hinge away from the column face. That can be achieved easily by just adding some other components, and they will strengthen that area, meaning that this area which is unstrengthened, unstiffened, will get the plastic hinge and the beam will rotate here. And the last concept, which is used quite a lot in the seismic design of steel structures, is where we are deliberately weakening specific areas at a distance from the column face. And for these we have the very widely used in the US RBS connections, the reduced beam section connections, as you see them here. The standard pre-qualified RBS joint is this one, with these curved cutouts from the top and bottom flanges, where this area is weakened and then the plastic hinge will be formed here. There are many different types of RBSs with some other dog bone cuts or penetrations on the flanges, and you will see a plethora of these in the literature. And more lately there is another concept, a very similar concept of the RWS connection, the reduced web section connection, which is something that I have worked a lot on the last 10-15 years, and the principle is the same. Of course, instead of having a moment hinge here, you have a shear hinge here because you are reducing the area of the web. It's not the right time to go through that. There is another lecture on this that I have done, so that you can watch later on perhaps. The last thing is the shear panel zone, as we discussed before. So in a beam to column connection, the web panels of the column must provide adequate overstrength to permit the development of the expected dissipative mechanism, avoiding the plasticization or shear buckling of that area. We don't want to get anything in that area because that will affect directly the continuity of the column, and then we will end up having high overturning moments of the column. So the design force in the web panel, due to the action effects over the minimum of the shear resistance of the web panel or the shear buckling resistance of the web panel, should be smaller than 1. And the last thing is the column foundation connection. which has to be designed in such a way to have adequate overstrength with respect to the column. In particular, the bending moment resistance of the connection must achieve the following relationship. So the MCRD should be greater or equal to 1.1 times the overstrength factor times the design plastic moment of the column, considering the axial force NED acting in the column that gives the worst condition for the base connection, times the NED. Explicit design guidance for beam-to-column connections in moment-resisting frames is available as a result of the huge international research effort made since 1995, which is when the Kobe earthquake happened, and in combination with the 1994 Northridge earthquake in the US, a lot has changed since then. So a table like this one is giving some recommended design values for specific types of connections. So you can check that reference and you can find different types of connections in different figures, and the maximum ductility class allowed for the European or US standards is given correspondingly. In the next few slides, we'll see briefly some information about the concentric braced frames and their detailing. So herein we are presenting again an X bracing and a V bracing, and you see also some nice pictures from real structures and how they look in reality. So the detailing rules for the concentric braced frames is that we have a global mechanism, and the dissipative elements are the bracings in tension. The concentric braced frames shall be designed so that yielding of the diagonals in tension will take place before the failure of the connections and before yielding or buckling of the beams or columns, as we discussed in the first part of the presentation. The global capacity design allows the formation of the global dissipative mechanisms. So the new thing here is that you see this NPL, which is drawn on the graph at the bottom, and you see that how a column buckling will look like in reality if it is not designed appropriately. So the local capacity design allows the formation of the local plastic mechanisms and ensures the transfer of full plastic forces. So here we have two connections. One was for the X bracing, the other is for the V bracing on the right. And what we are showing here clearly is which parts are meant to be the ductile components and which parts they're meant to be over-designed, over-strengthed. So on the left, you can see with the blue arrows that the beam and the column is over-strengthed, whereas as well as the gusset plate of the connection, whereas for the brace we have the formula as we've seen before, with the gamma RD times the 1.1 times the NPLRD. On the right hand side, again, we have the beam just above the gusset plate where the two diagonals are connected, and that part has to be overstrength, otherwise it will act as a link element. We don't want that. And of course, again, the gusset plate will be overstrength. As we saw before in some pictures, you may get some sort of deformation, elastic deformation of the gusset plate, but it should not fail plastically. And the diagonal members, they are designed in this case for tension and compression, again with the same rule as before. Looking at the diagonal members in structures of more than 2 stories, the non-dimensional slenderness of diagonal members should be in frames with X braces is between 1.3 and 2. In frames with V bracings should be smaller or equal than 2. So calculated over all the diagonals of the braced frame in order to satisfy a homogeneous dissipative behavior of the diagonals. It should be checked that the maximum value does not differ from the minimum value by more than 25%, so to keep the balance. The overstrength factor to apply the capacity design criteria is the omega, and is the ratio between the plastic axial resistance over the applied axial force. And when it comes to beams and columns, the following requirements is that the NED over NPLRD. The NPLRD is the design backlash resistance of the beam or the column in accordance to Eurocode 3, considering the interaction of the buckling resistance with the bending moment defined as its design value in the seismic design situation. So the NED and the MED are the formulae are given here. So this term must be smaller or equal than 1. And when it comes to the connections of the concentric braced frames, these connections have to provide adequate overstrength to permit the development of the expected dissipative mechanism, the plastic hinge, and the fillet weld or bolted non-dissipative connections. The following expressions should be satisfied: that the design resistance of the connection should be greater or equal to the overstrength factor times 1.1 times the plastic resistance of the connected dissipative member based on the design of the yield stress of the material, and that is equal to the upper bound of the plastic resistance of the connected dissipative member. So looking at the dissipative semi-rigid and or partial strength connections, which are permitted by the codes, provided that the adequacy of design strength, stiffness, and ductility is supported by experimental evidence. So different connections can be designed as long as we said before, they have been tested, like what we do for the connections of a moment resisting frames. Looking at the analysis of frames with X bracings, the standard analysis is made assuming that under gravity loading, only the beams and columns are present in the model, and under the seismic loading, only the diagonals in tension are present in the model. And this is again the same concept of having the distinction between the two systems. For the analysis of the V bracings, a standard analysis is made again assuming that under the gravity loading only the beams and columns are present in the model, and under the seismic loading both the diagonals in tension and the ones in compression are present in the model. Here we have two diagonals, one being in compression, one being in tension, of course. Where 0.3 is the factor used for the estimation of the post-buckling resistance of the diagonals in compression. This post-buckling resistance, it has to do with the capacity of the diagonal to further resist forces in reversed mode. So we're applying compression and tension in the same member, and there is a material degradation as we said before. So this 0.3 is the reduction of the capacity due to the local buckling that has happened in that member, and then the load is reversed, but there is a reduced capacity of that. Talking about the eccentric braced frames, EBF, we have seen them before with these seismic links in the middle, which are subjected to bending and shear. They're acting in bending and or shear forces, and the whole design is based on these elements, that they can dissipate energy by the formation of the plastic hinge in bending and or shear. So moving on, we also see a nice picture of a building that is using the link elements. So now these elements can be classified. There are three classification categories: the short links, the long links, and the intermediate links. The short ones, they dissipate energy by yielding, essentially in shear. They're more like compact sections. The long links, usually they dissipate energy by yielding in bending, and the intermediate links, the plastic mechanism, involves both bending and shear. And in the graph below, you can see the different types of these short, of these link elements, seismic link elements, and how we go about proportioning the design of these with some factors that we use here. In addition, we have some further rules for the design of these seismic links. There is one case where equal moments would form simultaneously at both ends of the link. As you can see on the left hand side, there are different rules that they apply for the short, long, and intermediate links. And there is also the case that only one plastic hinge would form at one end of the link, and the rules are herein different. Now, there are further rules that we use for designing the intermediate web stiffeners in those seismic links. As you have seen them before, and in real life, those are beam elements that they have many stiffeners, and for different things that we want to achieve, we use different set of web stiffeners. So here are some rules. That they are linking the rotational capacity of the seismic link. Efficient buildings, and you can see here on the top left some steel shear plates like we discussed before, but with penetrations in order to define a particular buckling shape and the ductility of that system. There are other kind of braces which are not BRBs in particular, but they act as BRBs because there are elements in tension and compression at the same time. There are, again, ways of strengthening the column by weakening the beams, but creating a fuse kind of plate where, like the seismic link, but this is not for a braced frame, is for a moment resisting frame. And that kind of component here can be used as a fuse. There are self-centering connections that they allow the opening and closing of the beams, and they come back to their initial state. And of course, different types of bracings and many other passive as well as semi-active and active systems that we use in steel structures to mitigate the inelastic drifts of the frames. So we're moving on to the composite steel concrete structures and the design. Here's very briefly the ductility that is needed in composite structural elements or in composite connections is achieved as in reinforced concrete by detailing the design so that the steel yields while the concrete remains elastic. In such a way, the integrity of the concrete is maintained during the seismic event, and the energy dissipation is achieved by the yielding that is taking place by the steel sections as well as the rebars. In dissipative composite structures that need reliable dissipative zones, two options exist. One is either to achieve ductile composite elements and connections by complying with certain specific conditions, or rely on the steel sections only and ignore any contribution of the concrete in the resistance of dissipative zones. So we see here three types. Type 1, the steel or concrete moment frame with concrete infill panels. We have the concrete walls reinforced by encased vertical steel sections, and we have the concrete shear walls coupled by steel or composite beams. Earthquake resistant composite buildings can be designed to one of the following concepts. The concept A is when we have low dissipative structural behavior, and the reference is only to Eurocode 4 with a static design for the analysis and the design. Concept B is more dissipative structural behavior with composite dissipative zones, and again reference to Eurocode 4 and 8 for the analysis and design. And concept C, which we have a dissipative structural behavior in steel dissipative zones, references to all three Eurocodes, Eurocode 3, 4 and 8 for the analysis and design. The design concepts are related to structural ductility classes and the behavior factors Q. And for these we have another set of tables for the different concepts. Of course, concept A is the low dissipative DCL, and the Q is again smaller or equal than 1.5. For the concepts B and C, the medium and high dissipative structure and ductility class, we are talking about Qs for about 4 or even different numbers as defined in the table below, based on the exact type of the composite structure that we've got. Again, we're using the ratio AU over A1, alpha alpha U over alpha 1, in order to define the exact number of the Q behavior factor. And here is a set of recommended material values for the class B and C. So you can see the concrete that is more or less suggested to be C30-35. The steel is the same as for the seismic design of steel structures, and the reinforcement. It's got a characteristic yield strength, minimum value of K, and characteristic strain at maximum force, depending on which class you're designing for. So for calculating the stiffness of composite sections, we have to look at the concrete, which is in compression, and we calculate for that a modular ratio N. And it is important to know that there are two bounds for calculating the plastic resistances. One is related for the checks that we need to do for the concrete and the ductile steel components. And the other one, the upper bound, is the one that will look in all the components, including those in the vicinity near the ductile zone, so including the welding, for instance. And don't forget that we are doing the analysis for both positive and negative moments. So we have to follow the recommendation, as you can see in the table below, when we do these calculations. Moving on, we are looking at the ductility in bending of steel beams acting compositively with slabs, and the general concept used to define the condition for ductility of composite sections is exactly the same as that used for the reinforced concrete sections. The strain diagram must indicate that strains in the steel reach the yield strain epsilon y, while strains in the concrete are still below the epsilon Cu2, the ultimate strain of concrete in compression. So again, there is a table that is giving us the values for the depending on the ductility class, and of course the Q factor, Fy and X over D upper limit is included. When it comes to the detailing rules, and in particular for the reinforcement, there is a local design of the reinforcing bars that is used in the joint region that has to be justified using the equilibrium models, and Annex C of Eurocode 8 provides the complete information for the design of the seismic reinforcement, and the design is dependent on dimensions and connection type. Moving on to the influence of the concrete encasement on the local ductility, and there is a table that is presenting again different ratios of the system, and that is attributing with different values under the DCM and the DCH categories. And these limits can be increased by up to 50% if details such as the straight bars and stirrups are followed. Looking at the composite columns, generally these are considered as non-dissipative structural members, therefore we use Eurocode 4 to design them. Columns may be dissipative at ground level in moment frames, and at the top and bottom of fully encased columns at any story. So we did see before some frames with plastic hinges, and as I mentioned before, I think that was in the first part of the presentation, there were plastic hinges at the bottom of the columns of the first floor. And for fully encased columns, so when you have a steel that is fully encased in concrete, then you have usually plastic hinges at the top and the bottom of that. Now, when it comes to the bond and the friction shear resistance, this is quite not reliable for composite members, and if we are talking about an insufficient bond stress between the two materials, then we use shear connectors. In most cases, for long columns, and especially if we use them in significant applications, shear connectors will be provided. We do not overdo it because there are issues with the concrete compaction, and of course is increasing a lot the fabrication cost. Now, for all columns in bending, we either design them as steel alone, or combined resistances of concrete and steel may be considered. When it comes to the shear, there is very limited research, so more research is required. At the moment, what we do is when we have fully encased members, then we use the concrete section resistance for the shear. When we have partially encased, we use the steel. And when we have a filled member, so it's a steel member filled by concrete, then we use either of the two. As you can imagine, all scenarios are on the lower bound, so we are under designing just so that we have a safe number, but we know that this is not really representative. Some further rules are applied when we have steel beams with slabs, and we have positive or negative sign of bending moment, and whether that is an interior column or an exterior column, we have different transverse elements, and we design the composite action and the steel reinforcement detailing differently according to each scenario. Looking at the steel beams with the composite slabs, we have for sagging moments, there is a requirement for achieving the connection degree of 0.8 or bigger, and when we have hogging moments, there is the design is based on the plastic resistance of the rebars. So as you can see below, the KR value is changing accordingly. So, looking at the moment resisting frames of composite structures, the global design objective for dissipative composite moment resisting frames is to form plastic hinges in the beams and in their connections, but not in the columns, exactly as we have for the steel structures as well. So the weak beam, strong column solution is also applied here. However, we do have plastic hinges at the base of the frame and at the top of the columns in the uppermost story, so at the very highest story. The design should be such that the plastic rotation capacity, it reaches the 25 mrad for ductility class M and 35 mrad for ductility class H. When it comes to the analysis of beams, there are two different stiffnesses. One is for the slab uncracked, and we're considering a positive moment, and one is for the slab cracked for the negative moment. So the equivalent inertia is calculated as the 60% of the first plus the 40% of the second. When it comes to the columns, again, there is an EI, which is calculated as you can see in the formula. Lastly, looking at composite frames with concentric bracing, the non-dissipative structural elements can be beams and columns of steel only or composite. However, the dissipative elements, the ones that we want them to buckle and provide the ductility to the system, they have to be steel only. The main two reasons for this decision is that prior to their buckling, composite braces would tend to overload the beams and columns, something that we want to avoid because they will create a lot of forces in the elements that we don't want them to be forced significantly. And the composite braces have not been the subject of in-depth study, and consequently there are uncertainties with regard to their cyclic behavior in both tension and compression. When it comes to composite frames with eccentric bracing, in principle it would be possible to use composite elements for all frame members. However, there are again some uncertainties associated with the composite elements that make them unacceptable for use in dissipative zones of eccentrically braced frames where large deformations are needed, rotations up to say 80 m-rounds.